Hello and welcome to iitiansgateclasses once again. So yesterday we were discussing about min heap and max heap. So first let's clear some concept about the heap. Then we will move on to min heap and max heap. Okay, heap is a very important data structure, and you should understand it very well such that if any question is given on the heap, it will be easier for you to answer. Okay, it's very important, but it's very easy also once you understand it. Okay. So if you know the binary tree, what is a binary tree? Where we have at max 2 children node. Okay, so this is also called binary tree. This is also called binary tree. Okay, where we can have at max 2 children. This is also called a binary tree. Okay, where we have only single node. At max means it could be 0, it could be 1, it could be 2. Okay, so these all are binary trees. But in case of a heap, we are saying that it's almost complete binary tree. Almost complete binary tree means at the last level, we may have some missing nodes, but a level before it, we have all the nodes like this. Okay. But what is a valid and invalid heap? This is a invalid heap. This is a almost complete binary tree, but we have assigned a children here before assigning to the left of it. Okay. So here we have nothing, here we have nothing, and then we are assigning it here. So whenever we fill the elements in a heap, first we will go from top to down and left to right. Okay, so this is a valid heap where we have some missing elements here. We have some missing elements here, right? But a level before it, we have all the elements, and we are going to fill the incoming elements from left to right. Okay, from left to right. Now let's suppose you are given with some elements like this. These are the given elements 0, 1, 2, 3, 4 till 14. So you are going to fill it like this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. First you will fill this level, then this level from left to right. Okay. Then this level from left to right, then this level from left to right. Now in a heap, if we try to represent the heap in a array, how can we represent it? Okay, so for a given data structure, we don't know like how can we represent the heap in our database. So we can represent the heap in our in a form of array. Okay, in a form of array. How can we represent it? We are going to fill the element like this. Now we can easily know that who is the parent of 7. Okay. For example, for 7, right now, the index of array and the element value are same. For the simplicity purpose, I make the index of array and the value of array same. Okay. Here we could have like 100. I don't care about the value. I care about the index position. The position is 7. Okay. So I want to know the parent of 7. I will say that 7 minus 1 divided by 2, take the floor of it. This index element, if this is the index of an element, I want to know the parent of it. So 7 minus 1 divided by 2, which is 6 by 2, which is equal to 3. So the third index element will be the parent. Third, okay, as you can see here, if this is 7, 3 is the parent. Okay, the third index element will be the parent. Similarly, pick any random number like 11. Okay, so for 11th position, I am not taking this 11, I am taking this 11, the index of the array. 11 minus 1 divided by 2, take the floor of it, and it will be 10 by 2 equal to 5. So you can see here that here I am representing number as index also, okay, because number and index are same. 11th parent is 5. 11th parent is this 5. 5th index element is the parent of 11. 11th index element. So this is how we can know the parent of each element. Similarly, if you want to know the children, then you can simply multiply like 5 multiplied by 2. 5, if 5th is the index, 5 multiplied by 2 plus 1. Okay, and 5 multiplied by 2 plus 2 will be the its left side parent. left side children, it's right side children. Right side children. Okay. Similarly, in 6, you can see that 6 multiplied by 2 plus 1 is left children, 13, and 6 multiplied by 2 plus 1 plus 2, which is equal to 14, is our right. So these are actually this using the array index only I can identify it. Okay. So for example, if you want to know children of this element, you will pick its index, do this mathematics, that the left side would be 6 multiplied by 2 plus 1, which is 13. Okay. So the 13th index number will be the left children. Similarly, we can calculate the right children also, like 6 multiplied by 2 plus 2. Okay. So this is how you can represent a heap in an array structure, array data structure. Okay. Now let's move on to mean heap. Mean heap. The very basic simple property of mean heap is it's a heap. First thing is it is a heap. And I explained what is a heap. I explained here, right? Then the second point is here any node value will always be less than its children. Okay. So this is a mean heap. So how can you represent a heap? Like this could be a valid mean heap. 2, 15, 3. Here we have 40, 50. Here we have 4, 5. Right. So see here that 2 is greater than all of its children. 15 is greater than 2 is smaller than all of its children, because it's a mean heap, not max. In max, the condition is reverse. Okay. Any node value will always be greater than its children value. 15 is less than all its children. 3 is less than all its children. Okay. So this is how you can basically represent a mean heap. Now there are some basic things for a heap you need to understand. For example, consider that you are given with a heap. You are already given with a heap. Okay. So a heap can be given in an array like this. You are given with an array like 10, 20, 30, 40, 50, 60, 70, 80. Okay. Sorry, 80, 81, 82, something like this. Okay. So now you have to construct a mean heap out of it. It is a valid heap first. So you have to construct a heap out of it. Okay. Let's say that you are given with a heap and you want to know whether this is a valid mean heap or not. You will simply put it like 10 here, then 20 on the left of 10 and 30 on the right of 10. 20, 30. Then 40 on the left of 20, 40, and 50 on the right. So you are filling it from top to bottom and left to right. Okay. Then we have 60 here, 70 here, 80 here, 81 here, 82 here. So it is a mean heap, as you can see, because all nodes have value lesser than its children nodes. Okay, 10 is less than 20 and 30, 20 is less than 40 and 50. Similarly, 50 is less than 82. So it is a mean heap. Now, if you are given that I want to insert an element, for example, it is given that you want to insert 5 in the heap. So how would you insert 5? You will insert 5 at the last position, like here. You insert 5 in array like here. Okay. Now I am writing down in the tree structure because it's easier to visualize. Okay. So if I'm performing an operation in tree, for example, I'm going to swap the 5 with 50. Why? Because 5 is less than 50, right? 5 is less than 50. That's why I have to swap 5 and 50. So similarly here, for the 5, I will calculate its parent, its current parent. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So 5 is is at 10th position. So who is its parent? It's 10 minus 1 divided by 2 and its floor, which is 9 divided by 2, 4.5, and the floor of 4.5 is 4. So at the 4th position, we have 50. So 50 is current parent of 5. Okay, so I will swap 50 and 5 in the array. So it's difficult to make you understand the operation in array. So that's why I constructed tree. Okay, but in real, this will happen in the array. In tree, I don't have to again and again calculate the parent and the children index, right? But in array, I have to do it. But in real programming, once you implement the heap using array, the swapping will done like this. You will calculate the parent of 5, then you will swap. Okay, so we want to find out. We want to again. Right now, this is not a min heap. This is not a min heap. And what we are doing insertion. We are doing insertion in a min heap. So for insertion, whatever element you want to insert, you will insert at the last location. So this is the last location right now. Then in the next step, what you will do, you will compare it with its parent, which is 50. If this element is greater than 50, then it's okay. Because in min heap, 50 is supposed to be greater than all of its children. Right now it's not. So 50 is supposed to be less than all of its children in min heap. Right now it's not smaller. So we have to swap these two. 50 will come here, 5 will come here. Again, we will do the same thing with 5. We will compare the 5 with 20. So we'll swap 20 will come here, 5 will come here. Again, we will swap 5 with its current parent. So 10 will come here, 5 will come here. And that's enough. Okay, that's enough. So right now, the current tree will look like something like this. After insertion and doing all the operations, the 5 will reach out to its position where it's supposed to be. So the tree will look like this. 5, 20, sorry, I will try to set it here. Okay. Yeah. So the resulting tree will look like this: 5, 10, 30, 40, 20, 60, 70, 80, 81, 82, and 50 here. So right now it also satisfies min heap tree constraints. So this is a valid min heap. 5 is less than all its children, 10 is less than all its children, 20 is less than all its children, and all it's satisfied for all the nodes. So that's how you can insert an element in the given heap. Okay. So right now let's move on to our next topic. But what is the time complexity of the insertion? If you are given, the condition is you are given with a min heap, okay, with some n element. Okay, you are given with a min heap with an element. And the second thing is you need to insert exactly one element in min heap. What is the time complexity? So for that you need to understand the basic structure of min heap, like what is the number of levels we are having in the min heap, okay, and how many swaps we will do in worst case, in case of insertion, how many swaps we are doing for insertion. Okay, for example, let's consider a min heap. I am just portraying the structure of min heap because you don't have to understand all the things, right? Like actual value to understand the time complexity. Okay, so in worst case, the height of the tree height of the tree, binary tree will always be height of min heap will always be order of log n. Why order of log n? Because it's an almost complete binary tree. Binary tree height can be order of n. How binary tree height can be order of n? If you consider a very simple binary tree, its height can be like this. If you arrange binary tree like this, we have n element, so its height is also n. Okay, height is equal to n. But this is not the case in min heap, because we are filling min heap like this. Okay, we can never make a min heap either like this or like this. This is not a valid min heap, as we already know that. Okay, so it's almost complete binary tree. So the almost complete binary tree height is always log n. I already explained many times why it's log n. Okay, I already explained while I was explaining asymptotic notations. I already explained why it's log n. Okay, so we need to understand this thing, that the height of a binary tree is log n. Okay, now once it's known that it's log n, the number of swaps we do for insertion. Okay, once we do the insertion, for example, if the tree is given like this and we have to insert the element, we will insert at the last position. Right now the last position is here, right? So what is the maximum number of insertion, maximum number of swaps you will do? It will be like one here, second one here, and third one here. These are the maximum number of swaps you will do, which is equal to height. So in case of insertion, the time complexity will be of inserting exactly one element equal to order of log n. Okay, it's order of log n in case of insertion. Now let's move on to our next operation of min heap, which is deletion. Okay, so in min heap, deletion is always performed at the root. Okay, you can't be given, min heap is a data structure where you can't simply say that I want to delete a like nth element. Okay, because it's the data structure. So somebody argues that what if I want to delete the middle element? Okay, that's not going to work. Min heap is not going to support that operation. In case of deletion will always happen at the root of the min heap. You always pop up the minimum element in the min heap. Okay, so that is how this data structure is designed. Suppose you are given with elements like 10, 20, 30, 40, 50, 60, 70, and 80, 90. Now you have to delete. You want to perform a deletion operation. So as I already explained, you will always delete root element, which is also minimum element. Okay, so you will delete this one. This element you will delete. But root can't be void, right? So you will replace it with last element. Now, what is last element? 90. You will always replace it with last element. Once you replace it with last element, what's going to happen? Again, you will do the same thing. You will compare it with its children, whichever is lesser. So in case of insertion, we are comparing children with parent. In case of deletion, we'll compare the parent with its children. Okay, whichever is lesser will be replaced here. So 20 is lesser. So 20 will come here, 90 will come here. again, we are going to compare it with this one. So 90 is not less than 40 or 50, which should be the property of, which is the property of min heap. Okay, so 40 is lesser. So right now what's going to happen, 40 will come here, 90 will come here. Now again, 90 have only one element, 80, because we replaced 90 with 10. So that's why 90 have only one children, 80, which is again less than 90. So 80 will come here and 90 will come here. So what is the resultant tree? It is 20 and 40 here, 30 here, 80 here, 50 here, 60, 70, and 90. So we successfully deleted 10, which is the root, and we maintain the properties of min heap. So how many swaps we will do? We will do order of log n. It's easy to understand, right? Because the number of swaps we are doing here are basically equal to the height of the tree, right? As you can see that 90 slide down to the bottom. Okay, so the number of comparison are basically 3 or I think it's 2 log n, which is equal to order of log n only. Why 2? Because we are comparing with this one and this one, then this one, this one. But we will swap it one of these two only. So that's why number of swaps are log n, number of comparison are 2 log n. So the total effort is 3 log n. As we know that in case of asymptotic notation, constant don't matter until constant are in form of like this. Okay, and k raised to power n or n raised to power k. We don't care about the constant. So the 3 log n is equivalent to order of log n. So in deletion also, the time complexity is order of log n. In insertion is order of log n, deletion is order of log n. Why? Because height of the tree will always be log n, order of log n. Okay. Now let's, there's one more very important thing. If you are given that, if you have to find the time complexity of creation of min heaps. So you are given with some random n numbers, random, or you can say jumbled n numbers. Okay, you are given jumbled n numbers, right? They are not sorted. Now you have to create a min heap. How much time will it take? So let's consider the insertion. For one insertion, it's taking log n. For n insertion, it will take n log n, right? But it's not correct. For one insertion, it's taking log n. For n insertion, it's taking n log n. It's not correct. If you try to construct a tree, like for example, you are given random number like 25, 77, 88, 19, 45, 35, 26. And each time you apply the insertion algo of min heap, it will take n log n. Okay, for example, you will do something like this. You will first insert 25. There is nothing in the tree, you insert 25. Then 77 came up. Okay, 77 is basically greater than 25, so we don't care. We'll insert it. Then 88. Okay, that's also good. Then there come 19. Once you insert 19 here, you have to compare. You have to apply the insertion algo where you compare 19 with the parent and swap. Okay, so 77 will come here. 19 will come here. Okay, again 19 is smaller, so we'll swap. 19 will come here. 25 will come here. Okay, so tree will look like 19, 25, 88, and 77. Okay, then there come 45. So you will insert 45 here because 45 is greater. Then there comes 35. Now 35 is smaller. So you will swap 35 with its parent. 88 will come here, 35 will come here. Now 35 is greater than 19, so you don't swap. Now there come 26. So 26 is smaller than 35. So 26 will come here, 35 will come here. But this algo is not best algo, not the best algo, because it's taking n log n time. N log n time. Let me tell you how. You can like roughly consider how it's n log n. Okay. For example, a tree is huge. A tree is huge. So how many nodes do we have at the leaf level? How many nodes? We are only considering leaf level. Okay. So suppose till here we have already constructed the tree. Till here we have already constructed the tree. Okay. How many nodes do we have at the leaf level? For example, these many nodes are remaining. 1, 2, 3, 4, 5, 6, 7, and 8. I'm just counting. We have 8 nodes, remaining 8 nodes. So we are about to insert 8 nodes. Compared to the whole tree, how many nodes do we have at the leaf level? At the leaf level, we have approx n by 2 nodes. Okay, let's count the all nodes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have total 15 nodes, out of which 8 nodes are at the leaf. So always remember that n by 2 almost. So it's actually at the total number of inner nodes are 1, 2, 3, 4, 5, 6, 7. So it's always 7, something like this. Okay. So at the leaf level, we will have one greater node. Number of nodes at the leaf will be one greater than inner nodes. So total inner nodes are 7, and total leaf node, inner node. Leaf node means they don't have any children. Inner node means they have 2 children. So 2 or 1. So at least one node can have 1 children in heap. So leaf node are basically 8. So this is almost n by 2, right? Almost n by 2. So even if you apply insertion algo for n by 2 nodes, we will have n by 2 log n minus 1. Okay, so we are considering only this much height. It's n minus 1, which is roughly around order of n log n. N log n is good, but not great, not the best, not best. How can we reduce this time complexity? Let's consider an example, which is called insertion or creation heap algo, something like that. Build heap, which is called build heap. Remember that this is called build heap, and which is actually order of n. Okay, using some mathematics, we can prove it. So I'm going to prove it that how is it order of n. First, I will perform the operation. Then I will show you like how is it order of n. Okay, let's consider a set of n elements, which are 25, 77, 88, 19, 45, 35, 26, 26, 7, 99, 17, 89, 15, and 3. So these many elements are there. First, we will randomly insert into the array, or you can say into the tree. So 25 will come here, then we have 77, then we have 88 here. We are not right now sorting this out. Like at each insertion, we are not applying insertion algo. We are simply inserting all the elements first, top to bottom, left to right. Then we will apply the algorithm. 26, 7, 99, 17, 89, 15, and 3. Okay. Now, in the build heap algorithm, we use something called min heapify bottom. Okay. How it's applied? First, we will insert all the elements into the tree, which will take order of n times. Okay, so you are picking a number and inserting it into the some array. Or if you are considering the original array, it will take order of one time. Okay, so that's good. Now we will start from the bottom. We will start from the bottom. Okay, we will start from the bottom, and we will say that whichever is lesser will come here. Okay, so right now you can see that the 3 is lesser. 3 is lesser. So we'll put 3 here and 35 here. Okay, for now we are going to consider only we will go level by level. Okay, first we will sort this level only. We again have to come to this level one more time, or like 2 more time, number of levels time. But let's see how it works. Now here 17 is the minimum. So 17 will come here, 45 will come here. Okay, we are comparing the root with like both the children with the root, whichever is minimum will come. Now 7 will come here, 19 will come here. Okay. So this is the first iteration. In the second iteration, what will happen? We'll go to this level, right? And here 3 is the minimum. So we will swap 88 with 3. Say that, okay, 3 will come here. 88 will come here. But now 88 is greater than 15 and 35, both of them. So again, we will repeat the same step. We'll compare the 88 with 15 as well as 35. So 15 is lesser in 15 and 35 and 88. So 88 will come here. Are you getting my point? So once you apply the algorithm at this point, okay, on these 3 nodes, you again have to check these 3 nodes also. Again have to check these 3 nodes. Once you apply on an algorithm here on these 3 nodes, again you have to apply the same comparison here as well as here. Okay, so not on the both side, actually, sorry. Not on the both side, whichever replaces 77, on that side only, we have to sort the things again. So right now, see that 7 will replace 77. So wherever 77 have replaced 7, we will apply the algo, we will compare the children there again. So 77 will be compared and 19 is smaller. So 19 will come here, 77 will come here. Okay. So right now we are at this level. Here the 3 is minimum. 3 will come here, 25 will come here. Now 25 will be compared with these 2, 15 and 26. Okay, 15 and 26. 15 is the minimum. So 15 will come here, 25 will come here. Now this 25 will be compared with these 2. We won't touch 26 because we haven't replaced 25 with 26. 25 will be compared these 2. So 25 is minimum between 88 and 35, so it will remain there. Okay. So this is how we can construct the tree. So at the end of it, it will look something like 3, 7. So I have to go back and check 15. Here it's 19, 17, 19, 17, and it's 25, 26, 25, 26. Okay. Here it's 77, 99, 77, 99. Here it's 45, 89, 45, 89, and 88 and 35. 88 and 35. So once we apply this algorithm, the step number 1 is insert all the elements in the tree as it is. From top to bottom, left to right. Don't apply any kind of algorithm. Just simply insert them. Then start from the bottom, which is mean heapify bottom. Mean heapify bottom. Apply this algorithm, mean heapify bottom. We'll start from the bottom where we compare these two elements with its parent. Okay. And the minimum will come here. The minimum will come here. Right? Similarly, we will do the same thing on these 3 nodes. We will do the same thing on these 3 nodes. Then we will see these 3 nodes. Okay, these 3 nodes. Whichever swaps with this element. For example, if this one is swapped with this element, we won't do anything because we don't have any children. If this element swap with this element, we will again apply the same algorithm on these 3. Okay, similarly, for example, if this element swap with this element, we'll again apply the same algorithm on these 3. Okay, so let's count number of the operations we are doing here. Number of operations we are doing here. Okay, using some mathematics, let's see that we have n given nodes. So you simply insert n nodes, something like this. Okay, and we go down. We have log n level. Log n levels we have. Okay, you know that in complete binary tree we have log n level. Then again we have something like this. Okay. Okay. So we know that at the bottom we have n by 2 elements. I already explained that the leaf level will have n by 2. So let's say that m is equal to n by 2. M is equal to n by 2. Okay, which is also n by 2 is also order of n, right? So right now we are starting that, we are saying that it's m. Okay. So now we will do all the calculation in form of m. Okay, in form of m. And all. Okay, so this is m. So now once we do all kind of swapping here at this level, so we are comparing these 3. This is we are doing like number of swaps. Let's count number of swaps first. Number of swaps. How many swapping we are doing? Actually, we are doing 2 comparison. We are comparing this one with this one with this one. So there are 2 comparison. One swap at max. Swap at max. And number of comparison are 2. 2 number of comparison we are doing. 2 number of comparison we are doing here. Okay. So this is for these 3 nodes only. Similarly, for all this grouping of 3 nodes. Okay. We are doing actually 1 swap at max and 2 comparison we have to do. Minimum 2 comparison. Okay. So what is the effort at this level? What is the effort at this level? The effort is m actually. If you see that the effort is m. M, which is a number of leaf nodes. M equal to number of leaf nodes, which is equal to n by 2. Okay. Effort here is n by 2. M. Okay. So let's move on to this next step here. In the worst case, we are going to apply this algorithm 2 times here as well as here. But the node reduces, the number of node reduces. Now let me change the color. At this level. Okay, so this level, number of nodes are m. Here, number of nodes are m by 2. Because 2 nodes have 1 parent, number of nodes are m by 2. Here, number of nodes are m by 2 square. Here, number of nodes are m by 2 cube till m upon 2 log n. At root level, we have m upon 2 log m, not n, log m, which is equal to 1 actually. Okay. So these many nodes we have. Log m level we have, okay, log m level we have, actually it's n, but we are indicating in form of m. So we have log m. Let's consider, we are doing all the calculation in terms of m, okay. So here we have number of node as m upon 2 by 0. Here we have 2 node have 1 parent, so it's m upon just half of m. Half of m is m by 2. Here we have half of these because 2 node have 1 parent, m upon 2 square. Here we have half again, so it's m upon 2 cube. So at each level, once we are moving at the above level, we have these many nodes. If at the leaf level we have m nodes, on the above level we have m by 2. On another above level we have m upon 2 square. At whenever we move above, we divide it by 2. So it's m by 2, m by 2 square, m by 2 cube, m by 2 till number of levels. Number of levels are log n, which is m upon 2 to the power log n, which is equal to 1. Okay. So how to calculate the time complexity? Okay. I have to construct one more tree because I actually messed it up. So let's say that what is the time complexity? It is number of operation we are doing at each level, and we sum it up. We will sum it up number of operation. Okay. So let's consider the swaps only, because comparison are 2. If we count the swap, we can say that suppose we count the swap as k. The comparison are 2k. So the total complexity is 3k. Right? Why? Because for these 3 elements, number of swaps are basically exactly 1. Number of comparison are 2. Right? For the whole tree, if we say that number of swaps are k, number of comparison are 2k, and total effort is 3k. So we are going to calculate k. Okay. We are going to calculate k. How we do it? Let's see. Okay. So here the effort is basically m. Number of swaps are maximum m, right? Number of swaps are exactly actually m by 2, not m. Right? Because we can swap as many parents as we have. Right? It's m by 2. But at this level, for example, here we also have values. All these are filled. At this level, what is the number of swaps? What are the number of swaps? First, we will do swap here. Then we can do swap either here or here. Okay. Suppose we swap this number with this one. So we can do either, we can also do the swap here. Right. So number of swaps are m by 2 square into 2. Okay. So at this level, if we move, number of swaps are m by 2 cube. It's actually as many parents as we have. Okay, so I calculated number of element at each level. We are doing number of swaps exactly equal to number of each element at the level. Here, number of elements are m by 2 raised to power 0. So number of swaps we can consider m by 2. Once we come here, number of swaps are m upon 2, 1. Once we come here, number of swaps are m upon 2 square into 2. Here we have number of swaps are m upon 2 cube into 2 square. Similarly, once we move above at this level, we have number of swaps as 2 raised to power log m multiplied by 2 raised to power log m minus 1. Okay. So let's add the whole thing. M upon 2, 0 plus m upon 2, 1 into 1 plus m upon 2 square into 2. Okay, plus m upon 2 cube into 2 plus m upon 2, 3, so 2 square. 2 raised to power 4 into 2 raised to power 3. and this goes on. If we take m common, it's 1 by 1 plus 1 upon 2 plus 2 upon 2 square plus, sorry, it's not 2 square, it's not 2 square, it's 2, then 3, then here we have log n. Let me construct one more tree for you. Guys, this is quite important. If you understand this thing, you can give an explanation that how build heap algorithm takes order of n and not order of n log n. If you want to understand, stick to this. Okay. Here we have number of operation as m by 2. Here we are doing exactly one operation, m/2 actually. Okay, multiply by 2. There is no operation at the bottom level. Here we are comparing this one with this one and this one with this one, and swapping at most one time. So it's 2 into 1, 2 raised to power 1 multiplied by 1. Here we are swapping at most 2 times. Once here, once here. Okay, either this one or this one. Okay, so 2 times we are swapping. But number of element at this level is m/2 raised to power 2 multiplied by 2. And at the above level, we have m/2 raised to power 3 multiplied by 3. So the number of swaps will be number of times we are moving the element down. We are moving the element down. Okay, so it's 3 level only. Once we are at the third last level, for example, if this is the level, okay, I have to construct. If this is the tree, how many swap at max we can do? Okay, one swap could be, sorry, one swap could be this one, another swap could be this one, another swap could be this one. So at max 3 swap we can do. At max 3 swaps we can do at max. And number of element are m/2 raised to power 3 are there. m/2 raised to power 3 elements. Similarly, at this level, we can do at max 2 swaps. The number of element are m/2 raised to power 2, so it's 2. So once we add this whole thing up, it is m/2 0 plus m/2 1 multiplied by 0, okay, multiplied by 1 plus m/2 raised to power 2 multiplied by 2 plus m/2 raised to power 3 multiplied by 3. It goes like this. Once we take m common, it's 0 plus 1/2 plus 2/2 square plus 3/2 cube plus 4/2 raised to power 4 goes on upon, it goes like 1/2 raised to power log n multiplied by log n actually. So this is approximately around m. Why? Because this is a decreasing GP. This is a decreasing GP. Geometric progression. The value of the decreasing GP is almost around 1, or you can say order of 1. It is greater than 1 actually, not exactly 1. It is greater than 1, but some constant value. So it is some constant value, I mean to say, which is order of n by 2. M, which is equal to order of n by 2, which is equal to order of n. Okay, this is how build heap algorithm can be calculated, which is order of n. Okay, so you have to be patient to understand this algorithm actually. Now, let's see that in a min heap, I want to get the minimum element. What is the effort? For example, 40, 50, 60, 70. This is the case, right? This is a min heap. The minimum element I can get in order of 1 because this is the minimum element. Okay, so I can get the minimum element in order of 1. I know that topmost element is the minimum element, so in order of 1 I can get the minimum element. So a second minimum element belongs at this level. So I just have to find out the level 2 element. Level 2 element, one of these 2 elements is the second minimum. So this will also order of 1. I just have to compare 2 elements. right? So the third minimum will be maximum between these two, which is 30. And if this is minimum, 20 is minimum, then we have to compare these three elements. So the third element, I will construct a tree. I will demonstrate like how am I referring third minimum. Third minimum will take three comparisons, which is order of 1 again. Okay, order of 1. So let's construct a tree. It's 10, some 20 here and 15 here. Okay. Now we have this is the minimum one, right? This is the minimum one. Then we have 16 here and 17 here. Okay. Here we have 30 and 40. So we want to identify third minimum. Third minimum. What is the procedure? Okay. This is first minimum. This is second minimum. Because we compared these two. Now the third minimum either is this is the third minimum or between these two third minimum here, right? So we have to compare these three elements. So right now you can see that 16 is the third minimum, which is at level 2. If this is 0th level, this is first level, this is second level. So this belongs to second level. Third minimum element belongs to second level. Okay. So whenever you want to find out kth minimum. Kth minimum means some constant number. If k is constant, min heap is the best algorithm. Min heap is best algo. Okay, min heap is the best algorithm. If you want to identify kth minimum, where k is constant, for example, third, fifth, 7th, 10th, 100th, 1000th minimum. So in case of 1000th minimum, the effort is 1000 only. Okay. What if we want to identify nth minimum or n by 2th minimum? This is not a great algorithm, because if we want to identify nth minimum, what we will do, we will run a single iteration of bubble sort. In case of nth minimum, we will run a single iteration. If you remember bubble sort, the maximum element, which is the nth element, will bubble up to the last index. We will just run a single iteration of bubble sort, which is order of 1, order of n. Or we can simply run a single scan and we can identify nth minimum. Okay. So this algorithm is great for kth minimum or kth maximum. In case of maximum, we will have max heap. Max heap is just opposite of min heap, where each element is greater than its children. Okay. So let's summarize the sorting. We have seen these many sorting algorithms. Okay, comparison-based sorting. All these are called comparison-based sorting. Okay, and this is in course of algorithm. In every competition exam, you will be asked with this comparison-based sorting. First one is bubble sort. Bubble sort, okay. Second one is selection sort. So in bubble sort, in each pass, for example, in the first pass, we will, the maximum element will be bubble up to the last index. Okay, in the second pass, the second maximum element will be bubbled up to the second last index. Okay, and how do we do that? By swapping between the maximum and its next element. This time we will do the swapping. if we found out the maximum element, we will do the swapping. In the selection sort, we will iterate the array. After the first pass, we will identify the minimum element index and we replace it with the 0th index. We won't do any swapping until the end of the pass. So here, the question is number of swaps are equal to order of n. Number of comparison is order of n square. Okay. So time complexity is order of n square, obviously, because we are doing comparison also. But number of swaps are order of n. Time complexity is order of n square. The third algorithm is insertion sort. In insertion sort, what we are doing basically is we are inserting element from right to left. Okay. So for example, in the first iteration, we keep the element as it is. In the second pass, we pick the second element, we compare it with the first element. If second element is lesser, we'll swap. Either we won't touch it. Okay. In the third pass, we'll pick the third element. We'll swap it till it reaches to the element where it is greater than that element. Okay. So this is the insertion sort. And this time complexity is order of n square. Okay. In the best case, the insertion sort time complexity is order of n. If array is, so this is best case. Here in selection sort, best or worst. Best or worst. Time complexity is order of n square only. Okay. In insertion sort, best case is array is already sorted. So this is order of n. The fourth one is merge sort. So it's best or worst, it's order of n log n. And the best thing is merge algo. Merge algo is used to basically combine two sorted array into one. Okay, and there the time complexity is order of n. Fifth one is quicksort. Most popular sorting algorithm, quicksort, which is order of n log n in case of best and average case. In worst case, it's order of n square. And sixth one is heap sort. It's always order of n log n. In best case, it's order of n where elements are already sorted. But in average or worst case, generally they will ask you worst case time complexity. It's order of n log n. Okay. So this is the end of the divide and conquer and other kind of algorithms. In the next lecture, we will see greedy techniques. This is going to be simplest part of the algorithm. You just have to remember the algorithm. Okay. Basically, you will be given with some steps, and you have to remember those steps. Like, okay, if we follow these steps, we will have a best or you can say optimal algorithm. But greedy techniques are applied on certain given problems only. It's not applicable to all the problems. Okay, remember this. So in the greedy technique, we will see job sequencing. Second one is knapsack. Knapsack problem. This is not 0-1 knapsack. This is basically where we can split the item. This is not 0-1. 0-1 is dynamic. I will be explaining dynamic programming also. Okay, and the third one is half-man encoding. Half-man coding. Okay, or encoding. Fourth one is optimal merge patterns. And fifth one is minimum cost spanning tree. First, we have to understand what is a spanning tree. Then what is minimal cost spanning tree. So here we have two algorithms. PIMS and Kruskal. Sixth one is Dijkstra algorithms. So it's single source shortest path. Dijkstra algo. Most important one is this one, Dijkstra algorithm. Then we have something like BFS, breadth first search, depth first search. Okay, breadth first search and depth first search. So we will be covering all these algorithms in greedy technique. I will try to cover in like 3 lectures all the greedy techniques. So after that, we can move to the dynamic programming, which is the most interesting part, because in the interview question, you will always see a dynamic programming question there. Okay, some people consider it most difficult, but I consider it easiest thing. Once you know the recursion, it will be easier for you to understand dynamic. The core of dynamic is recursion. Then you introduce some memory element. You will understand once I explain. And thanks all for joining. So I'm ending this lecture here. Thank you.